Hello, boys and girls. Here we are in section 8. This is actually the last one we covered before our test, and it seems like it's so much, but this is our first step into what they call power series, okay? And that's going to be it. It's actually doable. This section is pretty straightforward, but there's things to understand. I basically write in the introduction, hey, we're going to use polynomials to approximate other functions that are not polynomials, such as, the trig functions, the sine wave, the exponential e, things like that. What I have here also, and I know I've mentioned it, is there's a video on 3 blue, 1 brown. If you Google that and go select Taylor's series from the author's Essence of Calculus series, it's a pretty good motivator. It's I know it's optional. You don't want to go see it, but you might want to check it out to see why it is we're in this chapter in calculus studying series. It's a good reason. So the topics in here are what the heck is a power series and when do they converge, and then we'll talk about, in a second video in this section, we'll talk about a couple more examples on intervals of convergence, okay? So first, what is a power series? And I wrote this up this morning and I just go, you know what a power series is it is this. What the heck is that? Here's the sigma notation for it. What they're doing in this case is they are including right there a variable in the definition of your series, okay? And so when they do that, the variable is always stepping up in power. So you've got x, then you have x squared, then you have x cubed. You know what that is? It's basically an extended polynomial. It says go forever, which is a hard concept to dream up, because that's not what we are able to do on this planet, is go forever somewhere. But we can go far. We can go as many terms as you want. We can go out hundreds or even thousands of terms if you want to. Okay, here's another example, okay, but the difference is it's not x, it's x minus a taken to a power, okay, and it creates a polynomial, okay. So for example, I'll give you an example of one that says, look at this, okay, so this is an example here, and it looks like 1 plus x squared over 2 factorial, and it keeps going. You can dream up the next one is x cubed over 3 factorial, x to the 4 over 4 factorial, etc. And here's the thing about power series is you can plug numbers into them. Okay, so if we plug the number 1 in for x, that means for every x that you see, you plug a 1 in, a 1, a 1, and it creates this series. Okay, now if you add up enough of these terms, like if you look at the sequence of partial sums, S1 is 1. S2 is 1 plus 1, which is 2. S3 is 1 plus 1 plus 1 over 2 factorial, which is 2.5, and you keep going. But the magic is, eventually you are heading towards E, which is equal to 2.71828, etc. No one's proving that to you right now. I'm just saying that's where it goes. Interesting. A polynomial, you plug in 1, and it heads towards E. Actually, E to the 1. What I know, and you're going to learn after this next test, is this is actually the series for the exponential E function. Okay, and we'll get to that. But here's another one to play around with. I also know about this guy, and I go, why don't you guys, with a calculator, plug in the number pi over 4 for x. So we have this series, here it is. Here's the formula for it. It's alternating, and x is going up by, double powers, so to speak. And you see it happening right there. 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. And it would go x to the minus x to the 6th over 6 factorial plus as many terms as you want. So I'm asking you now to pause and just plug in the numbers. What if we plug in x is equal to pi over 4? Okay, I'm pausing. Okay, you do it, and then you can pause the video. But then you would write, okay, so if we do that, we get 1 minus whatever we plug in. I want you to get used to this idea, plugging in numbers into these power series. 4th power over 4 factorial, maybe one more, 6th power over 6 factorial, plus, and as far as you want to go. The number we're plugging in is pi over 4 for some reason. Pi over 4. Pi over 4. Okay. I happen to take the liberty of crunching those numbers, and what you have is S1 is 1. S2, where you add the first two terms, is 0.69157, 0.69157. These are going to be irrational because pi is irrational, but that's okay. S3, first three terms added up, I got a 0.707429 and other change. And S4, when we add up all of them, all four of the first terms, we got 0.707103 and change. Okay, I don't know. I chose this one to goof around. We wonder, is it converging? Is it converging? By looking at the sequence of partial sums, here's the first one, here's the second, etc. But look at the last two. It didn't change much. And the next term you add is even smaller. So those terms at the front end, these 7071 or whatever, they're going to kind of settle into place. Yeah, I have a feeling it's converging. I also know it's converging because I know more than you. What I know is that this is actually the series for cosine of x. And what we plugged in was pi over 4. And as everyone knows, cosine of pi over 4 is radical 2 over 2. Take out a calculator right now, crunch it, and what do you get? My calculator says 0.707106781, 06781, and then it goes forever, okay? But look at, after adding only 4 terms, we are already correct out to 1, 2, 3, 4, 5 decimal places. It's converging towards cosine of pi over 4. Pretty cool. Pretty cool. That's the introduction to power series, at least on this tiny little video. We're going to do one more example and then stop this video and go do another one and continue the story. But that's what power series are. You create a polynomial by having a power of x or x minus 4 or x minus pi over 2 or whatever, and just go through the series. But our goal, of course, is to create series that actually we feel will converge towards known series, known functions. Easy for me to say on a video. Okay, so let's go to the next example. This one has nothing to do with anything. How can we be sure a power series converges and when does it converge? This is a good little discussion here I typed up. Well, taking a look at this series that I claim is for e to the x, it definitely converges for x is equal to 0, right? Imagine plugging in 0 for x all the way down the line. What do you get? 1. Oh, by the way, what's cosine of 0? 1. Pretty cool, right? Not convinced, I know. The other series, this one where, and this is just a generic one, this guy definitely converges when x is equal to a. So I would put in, if x is a, you get a minus a, right? A minus a all the way across, and it converges to the first number, C0, whatever that is. Okay, so for convergence, we want to know that it converges. The reason that they change this x to x minus a will become more clear later. But it's about centering your series somewhere that you're interested in. If you want to approximate a function, say sine wave, but you want to do it at, say, 3 pi over 2 instead of 0, then your a would be 3 pi over 2. And that comes later. We won't worry much about it. What we want to be able to do on this next test is figure out intervals of convergence. So the question is, oh, by the way, those cases where it does converge, it always converges for some number, 0 or a. But how about other values of x? So the question is, here's an example. What do we do to figure that out? Ready? Always, we do the ratio test. Why the ratio test? Well, you see the power, the exponential going on? The ratio test is good for knocking that out. So here's your first example for finding where it converges using the ratio test. How does it go? You go lim, as n goes to infinity, put some absolute values around it. What happens to the minus 1 when you put absolute values? It melts away to 1, doesn't it? And disappears. So all I'm worried about is x to the n plus 1. Remember, it's the n plus first term over the nth term, which lately, hopefully your homework, you're inverting and multiplying to speed yourself even more quickly along. This is what I get for my first step. I've done the ratio test quite a bit, you would imagine, right? But the best part is canceling stuff. Right here, this x to the n cancels with all of them except 1 power of x. And that's the only cancellation I see. So I have lim, n going to infinity, we have an x times, and then we have n squared over n plus 1 quantity squared. Where does that limit go? You should know downstairs is n squared plus 2n plus 1. The lead powers dictate it goes to 1. So we have a limit that says absolute x times 1, right? Or absolute x. Now here's the best part. You ready? All right, so we ran the we ran the ratio test to find the limit, okay? And we got absolute x. Question, when does the ratio test say that you have a convergent series? What is the condition? You ready? Answer, the limit is less than 1. So we force convergence on this guy to see what happens, okay? And so in this case, when we force convergence, we have the following condition. And what that does is it restricts x. You, as a series builder and user, can plug in any number for x because x is a variable. The polynomial is your function. But you're going to want to know, when I plug in a number, this is something that doesn't occur to us, but as mathematicians, and you get past this, you'll look back and go, yeah, duh, I can't just plug in any number. If it doesn't converge, then so what? I want to know when it converges. The ratio test is the way to go. And at the end, we force it less than 1, and that makes x behave. It puts a restriction on x for convergence. Ready? So what we have is absolute x is less than 1. Algebra 2 says, well, that means you're bookended between -1 and 1. And right now, folks, you're staring at your interval, what they call the interval of convergence. Okay. We could go through all the numbers in the universe and plug them in for x and go, that one converged, that didn't, that one didn't, that did. And be like, I don't know, Buddy the Elf looking at the Jack-in-the-Boxes for forever, testing every number in the universe to see if it converges or not. And instead of doing that, we're going to use our intelligence and use the ratio test. What that does, it says anything that's beyond -1 or 1, it diverges. But if you're in between -1 and 1, it converges. Awesome. Good to know. Okay, there's one more thing, though. Here's the last thing. What about the actual numbers -1 and 1? We have to, in this case, this is part of the homework, test the endpoints. It just makes things complete. It might be important, okay? Okay, so taking a look at that, you take your series down, which is now, the series, remember, is this guy. N is 1 to infinity. Yes, you got a -1 to the n. You've got x to the n, and then downstairs you have n squared. Imagine plugging that number in for x, that, like for instance, -1 or 1 for x. So that looks like the following. Our series, if you do that, and actually you don't have to write this down, but I did, -1 to the n, whatever you plug into the n, all over n squared, and what we'll plug in first? How about -1? Okay. If you're testing the other guy, and you have to, you'd have series n is 1 to infinity again, and it's going to be -1 to the n, and whatever you're plugging in to the n over n squared, and this time the number over here is 1. That's what it looks like to test every number. But thank goodness we only have to test 2. All right, so there's a weird thing. Let me ask you, here's a weird thing about what we're looking at. -1 to the n, -1 to the n. What can you do with that? What can you do with that? Well, what happens is -1 to the n times, I think of something like this. A to the 3 times b to the 3 can be seen as a times b to the 3. -1 to the n times -1 to the n is -1 times -1 to the n, but that simplifies to 1 to the n, which becomes 1. So all of this is just 1. Or you can think of it as -1 to the n squared. Anything squared is positive. And of course, we're dealing with ones. I know, man, that just made your head spin a little bit. But really, this just becomes 1 over n squared. Look at that. Converge or not converge? That is the question. The answer, it's a p-series. Beautiful. And it converges. Okay? Awesome. So you go up to your interval of convergence and you write a little mark under that saying -1, it converges. See, we're trying to find out the interval of convergence is what numbers for x cause convergence, and the rest wouldn't. They'd cause divergence. In this case here, you can play that same game, or you can just recognize, you know what, 1 to the n is just 1. So this series, actually, when you plug in 1, it doesn't change. The x just disappears, and you've got this n squared like so. Okay? Now, there's two ways to go about this. When you can go, hey man, that's an alternating series test problem. Or, if you're super duper, and this doesn't always happen, since this guy converges, you could say this series converges absolutely, which implies converges also. Now, sometimes what happens is this guy over here diverges, then you would have to run the alternating series test. But in this case, we'll use the theorem that says if a series converges absolutely, it implies series converges. Okay, that's a theorem. So they both converge. We march up here and we put a little mark under that guy too. Sometimes it's one, sometimes the other, sometimes it's neither. But what we'll do is in this problem, we'll proudly say my interval of convergence is, I'd say -1 to 1 maybe. That looks really pretty. And this video is over. I got a couple more to show you, but that gets you started. That's how you do it. The next two examples are pretty much the same. I'll give you a little more information to go by, and then you'll master this section. See ya.